Hello and welcome to this clip on the ionic product of water, Kw, and its influence on strong bases. We'll take you through the dissociation of water, the equation, and the fact that it's called the ionic product of water, and the relationship between this ionic product and the concentrations of H plus and OH minus in aqueous solution. And on the assumption that strong bases dissociate completely, we'll have a look at how we can calculate the pH of a strong base using the Kw expression. So this clip will assume already that you're comfortable with the pH scale and the implication that a change of one pH value is equivalent to a tenfold change in the concentration of hydrogen ions in aqueous solution. So essentially water dissociates into hydrogen ions and hydroxide ions. It's a unique equilibrium because H plus and OH minus are produced at the same time. It's the only reaction that does this. So the increase in H plus concentration means that the pH value of water decreases if it dissociates, but it remains neutral overall because of the equimolar quantities of OH minus produced simultaneously. Obviously, being an equilibrium, one direction will be exothermic, the other direction will be endothermic. In this particular case, the forward reaction is endothermic, so that means hotter water is more dissociated. The position of equilibrium is shifted to the right at higher temperatures. So if you were to measure the pH of hot water at maybe 50 degrees centigrade, it would be around 6.3 because of a greater proportion of H plus present. But it's important also to remember that the position of equilibrium will remain well to the left at all temperatures. So in essence, water doesn't really dissociate very much at all. So the degree of dissociation of water does not influence the general pH level to a great degree. If we look at water setting up a conjugate acid-base system, what it does is you get two water molecules that turn into one hydronium ion, H3O+, and one OH- ion, OH-. We take the equation in the box at the top and we write it down as 2H2O, giving you H3O plus OH-, but we also assume that H3O plus will dissociate further into H plus and H2O. We can cancel out and end up with what's in the box at the bottom of the screen, which is essentially the same as the dissociation of one molecule of water. Now, because water dissociates to form H+, it means that water can act as a very weak acid. But in actual fact, very little water actually dissociates like this. So most water actually remains as H2O, so it is a very weak acid. So for this reason, we assume that the concentration of undissociated H2O remains pretty much constant. Because water is an equilibrium, its dissociation will have a Kc value. And this is called the ionic product of water, or Kw. So writing out the Kw expression, that gives you H plus concentration times OH minus concentration over H2O concentration, which if we were to work out the units for it, it would involve some cancelling. However, because the concentration of water is massively larger than either the concentration of H plus or the concentration of OH minus, because of the fact that water doesn't dissociate very much in reality, we disregard it, we consider it mathematically constant, because it's so much bigger in any circumstances than either H plus or OH minus. It doesn't actually make a difference to the H2O concentration, what happens to the other two. So we effectively regard Kw as the product of the concentration of hydrogen ions and the concentration of hydroxide ions. So that means the Kw expression is H plus times OH minus, and the value we assign to this is 1 times 10 to the minus 14 moles squared decimeter to the minus 6. And this value is provided on your data sheet that you get in your exams. So we can use the kW expression easily in pH calculations for bases, because we'll obviously have the kW value from our data sheet and we'll be given the concentration of OH minus from the concentration of our base. So let's take a typical example such as 0.1 moles per decimeter to the minus 3 of sodium hydroxide solution. We can assume that it dissociates completely. So that means we can assume that the OH minus concentration is 0.1 moles per decimeter to the minus 3. But the pH is worked out using the concentration of H+. This is where kW comes in. If you rearrange the kW expression to make H+ the subject, or H+ concentration the subject, you can then divide the kW value, 1 times 10 to the minus 14, by the concentration of OH minus, which in this case is 0.1. That gives us a hydrogen ion concentration of 1 times 10 to the minus 13 moles per decimeter to the minus 3, and therefore the pH being plugged in to the pH expression at the bottom left hand corner of the screen gives us pH 13.0, what you'd expect for a strong alkali. So let's now try a practice exam question. This particular question applies the kW idea to sewage plants, because in sewage plants biological activity can be reduced by increasing the pH of the water. So the less acidic the water is, the less the bacteria and microorganisms are able to reproduce. So what they do is they add small amounts of solid calcium hydroxide, as the question suggests, and to the sewage water. So the reason it tells you that you can assume that measurements being made at 25 degrees centigrade is that the kW value that they give you in the question, which I've just highlighted for you, holds true, and therefore you can use that value in your calculations. So the first two parts of the question in part A are pretty easy. Obviously by now you should know that kW is the ionic product of water, and the expression that we use for it is the concentration of hydrogen ions multiplied by the concentration of hydroxide ions. So let's move the page down a little bit. And it says that a chemist checked the concentration of aqueous calcium hydroxide in the sewage water by titrating it with hydrochloric acid at 5 times 10 to the minus 3 moles per decimeter to the minus 3. So the chemist titrated 25 centimeters cubed of the sewage water with 21.35 centimeters cubed of HCl to reach the end point. So the first thing I'm going to do is I'm going to highlight the data that I'm given. So as in any titration calculation, the first thing you do is you think to yourself, what can I work out the moles for? So we don't know how much calcium hydroxide there is in the sewage water, but we do know that it took 21.35 centimeters cubed of HCl. So that's where I'd suggest that you start. So using N equals C times V from your first year of chemistry, we do 21.35 over 1,000 to convert into decimeters cubed, and then you times it by the concentration given, which was 5.00 times 10 to the minus 3. That gives us 1.067 times 10 to the minus 4 moles of HCl. Now working out the moles of calcium hydroxide is easy, because the equation tells you that there's a 1 to 2 mole ratio. So this will give you 5.335 times 10 to the minus 5 moles. And rearranging the N equals C times V formula so that C equals N over V, we take 5.335 times 10 to the minus 5, and we divide it by the volume in decimeters cubed, which is 25 over 1,000. And because I didn't plan ahead very well and didn't leave enough room to put the answer in the answer line, I've put concentration of CaOH2 equals 2.134 times 10 to the minus 3 moles per decimeter to the minus 3. And I've underlined it just to draw the marker's attention to the fact that that is my final answer. Obviously when you do this, you'll be much better at forward planning than I am, and you'll be able to make space, or at least write in small enough so you can put your calculation in there. So let's go on to the next part of the question. So this time it talks about what happened when a chemist analysed a sample of the water from another part of the sewage works, and it was found that the calcium hydroxide concentration was 2.7 times 10 to the minus 3. And it tells you that solid calcium hydroxide dissolves in water and its ions completely dissociate. So bearing in mind the 1 to 2 mole ratio between calcium hydroxide and hydroxide ions, the concentration of calcium hydroxide is going to be half that of the concentration of OH minus. So we write out the Kw expression first of all, and we put in the value like the data sheet would have told us in the exam. And the next thing to do is to rearrange it so that H plus is the subject. And that gives us an H plus concentration of 1.85 times 10 to the 12 moles per decimeter to the minus 3, which if you plug into the pH expression, pH equals minus log of the concentration of H plus, that gives us a pH of 11.73, which is what you'd expect for a strong base like calcium hydroxide. So let's move the page down a bit and look at the final part. So to be able to appreciate how to do this question, you have to look carefully what it's asking. It's asking about the pH, and it's doing it in terms of the difference in concentration between OH minus and H plus. So we've got to go right back to the beginning of the pH scale to be able to deduce what to do. So if we lay out the pH scale, what we can do now is populate each of the pH values with equivalent H plus and OH minus concentrations. So if we look at the H plus aqueous concentration in moles per decimeter to the minus 3, we get these values, and you can see that they decrease by a factor of 10 each time. So doing the equivalent for OH minus, so you can see that as you go from pH 0 to pH 14, the H plus concentrations decrease by a factor of 10 each time, and going back the other way, from pH 14 to pH 0, the OH minus concentration decreases by a factor of 10 each time. So what you've got to find is at which point is the H plus concentration 100 times smaller than the OH minus concentration. So at the point where 10 to the minus 8 is the H plus concentration and 10 to the minus 6 is the OH minus concentration, that's pH value 8. So 10 to the minus 6 times 100 equals 10 to the minus 8. So hopefully you found this a fairly useful clip. Please feel free to ask any questions of your teacher, or maybe coming to see one of us in a subject extension. But for now, thanks for your time, and see you soon. We've got the ionic product. I would maybe prefer to say ionic product of water, just to be on the safe side. We got Kw. We got 1.067 times 10 to the minus 4. We did the mole ratios to get 5.34 times 10 to the minus 5. And we got 2.137, I think it was, thereabouts, to get our third mark. Moving the page down a little bit, we got 5.4 times 10 to the minus 3, because we used the correct mole ratio of 2 times 2.7 times 10 to the minus 3. Dividing Kw by OH minus concentration gives us 1.85 times 10 to the minus 12, and we got 11.73 for that third mark. And we got 8 as our final answer. So maybe a slightly harder question than originally thought. Only 9 marks, but some of those marks you had to work quite hard for. So hopefully this was a fairly useful introduction to the idea of ionic product of water,
and its connection to the pH bases. If you have any queries, please jot them down and bring them into one of us in a subject extension, or perhaps have a chat to your teacher when you're back in college. But in the meantime, thanks for your patience, and see you soon.